In this video, we're going to look at how to conduct a confidence interval for one population mean, but this time when sigma is unknown. And I want you to think about this for a second. Think about why we were conducting a confidence interval. Because we don't have information about the population, correct? So we're using the mean from the sample to make a prediction about what interval that population mean is going to fall in. In real life, though, because in the previous video, we were working this out with the assumption that we knew what the standard deviation of the population was. We knew sigma. But in real life, if we knew the population standard deviation, would we need to conduct a confidence interval to estimate mu, or the population mean? Because to get the population standard deviation, if you remember how to get a standard deviation, a vital part of that is knowing your population mean. So in real life, normally we would not use our z-test statistic, our z-statistic, unless we had very large samples, and we'll see that in a second. We have this new curve now called a t-curve. T-curve looks very much like a z-distribution with one major difference that we're going to get to in a second. T-curves came up for a couple different reasons. So first of all, it's very much the same in that the area under it is equal to 1, so you can use the idea of symmetry, and you understand that the entire area is 1, so if you know part of an area, you can subtract from 1 to get the other part. It extends infinitely on both sides, approaching but never touching the horizontal x-axis. It is symmetric around 0, just like our normal distribution. But here's one major caveat. The t-curve depends on this new term called degrees of freedom. Degrees of freedom are related to sample size. In fact, you will see for what we're doing in Chapter 8 for when we're dealing with one population and looking at a mean, the degrees of freedom is simply equal to n minus 1. So our t-curve tends to be very narrow when we have very small degrees of freedom. But then, as the degrees of freedom get larger, our t-curve starts to look exactly like our normal distribution. And what the t-curve also allows us to do is work with incredibly small samples, like samples under 10. It was actually developed, oddly enough, to improve the taste of one of the world's oldest beers, Guinness. Someone who worked for the Guinness Company needed to do small batch samples, and he developed, because at the time only the z-distribution existed, and he developed a t-curve to tweak those values so that they were dependent upon the sample size. And he could do it for very, very small samples. The Guinness Company wouldn't allow him to publish under his own name, so it became called the student's t-curve. So your t-distribution, here's a small page of your t-distribution, is a little bit different from the normal curve because it's going to change values as you change degrees of freedom. So for example, if we were doing a 90% confidence interval, you had 0.90 in the middle, and you split it and had 0.005 on each side, that t of 0.05, the value you would use, t of alpha over 2 instead of z of alpha over 2, is going to change dependent upon the actual sample size. So if our sample size was 14, our degrees of freedom becomes 13, and we would use the number t of alpha over 2 would be 1.771. And if you recall, notice as the degrees of freedom increases, this value starts to go down. If we take a look at the regular table, and if you recall, z of alpha over 2 for or z of 0.005, sorry, let's change that. If we were using I don't know why I was writing 0.05. I apologize for that. Let me erase this for a second and draw a better curve. Again, I apologize. Sometimes I just write a little too sloppy. So z of 0.05, if you recall from the problems we just worked out, was about 1.645. But for a t-distribution, it's going to depend on the actual sample size. So let's look at the full t-curve for a second. Go to your formula sheet. Erase what we worked on before. Go down one more. Here it is. Sorry. So here is our column. I'll highlight it. Okay, here's the one we're working off of. Notice it keeps getting lower and lower as our sample size increases. Okay, come over to the next one. Continues to get lower and lower, and as we get really large, so notice at 100 it becomes 1.660. At 2,000 it reaches 1.646. The z-score is 1.645. So basically what's happening as your sample sizes increase on a t-distribution, the values become the same as your z-values. So that's why this table is here. It's also a great resource when you need quick z-scores, but for t-scores you have to go through this whole thing. Okay, so it's done a little bit differently because again you're going to have a different t-score for each degrees of freedom. People often ask, what are degrees of freedom? And why is sample size minus 1 called degrees of freedom? And the best explanation I can give you is to think of it this way. Let's just say you had, I don't know, 5 baseball caps, and you wanted to make sure you wore a different one each week, right? So your sample size is 5. Now on day 1, you wear, how many choices do you got? You got lots of choices on day 1. You got 5 different choices. So you have choices on day 1. On day 2, you still have this freedom to choose because you got 4 hats left. On day 3, you still have a freedom to choose. On day 4, you're down to 2 hats left, but you still have a freedom to choose between the 2. What happens on the 5th day? Do you notice you have no choice? You're left with what you have. So degrees of freedom kind of work like this. If our sample size is 5, our degrees of freedom is 4. Okay? Degrees of freedom will change a little as we work through different types of problems in statistics 2, but in stat 1, again, since we're dealing with just one population, degrees of freedom, you're always going to think of it as n minus 1. But if you go on to stat 2, or you're in stat 2 right now, you know, degrees of freedom is going to change depending on the type of test we're actually doing and how many populations we are working with, because we're going to work with multiple populations at times. Okay, so let's go back. Now, I want you to look at the formula. Notice it really doesn't change that much. We have the same assumptions, random, normal population, or large, but now sigma is not known. Because we don't know sigma, we have to use a different point estimate. We have to use a point estimate. Remember, when you don't know the population parameter, you use a sample statistic as a point estimate for that population. So we're going to use our S value, which is our standard deviation of our sample. So two things change. Our Z changes to a T. That makes sense. And our sigma changes to an S. Other than that, all the same rules apply. The formula is very similar. Let's look back at the formula sheet itself. I'm going to scroll up, go to chapter 8. There it is. Okay. And the formula sheet is very clear. Use a Z interval for mu when sigma is known. And then over here, a T interval for mu when sigma is unknown. And there's your formula with the addition of the degrees of freedom. So you can find it quite easily on your sheet. So let's work out a problem. Again, I suggest you hit pause and just try this on your own first. And try and jot down the correct information and see if you can come up with the correct T alpha over 2 before you. Okay, digital viewing times. As you look through this problem, you see that your N is 20, X bar is 5.16, because 20 adults. And here's where you need to be careful, because you're going to have to read a problem and know, well, are they giving me the population standard deviation, or are they giving me the sample standard deviation? So you got to read the problems very carefully. In this particular problem, or I should say in the last one that we did, it actually said the population standard deviation. In both of the last ones we did, it was very clear. This one has the words, a random sample of 20 adults spent an average with a digital media with a standard deviation of, so it doesn't say this is the population. This is coming from that random sample. So you've got to be careful. When the standard deviation comes from the random sample, it's just simply S. We want a 90%. And the second you write down an S, that tells you that you also need degrees of freedom, which are N minus 1. So we're going to do 19 degrees of freedom. Now the first thing we need to look up is our T value. So let me draw a picture. Okay, so we have 0.90. So then when you split it, your alpha, of course, is 0.10, because it's 0.1 minus 0.90. And then that needs to be split in half. Alpha over 2, we have 0.05 in either side. So I need T of 0.05 at 19 degrees of freedom. So T of 0.05 at 19 degrees of freedom. I know I'd have to go to my formula chart, my T chart on my formula table, go all the way down to T. All right, you want T. 0.05, I still have it highlighted. So let's go to 19, and 0.05 is 1.729. So we're going to use 1.729, our T of alpha over 2 is at. Then we just need to plug it into the formula. 5.16 plus and minus 1.729, 2.3 over square root of 20. Just like before, always get this value first. That's 0.88. I get 0.889. Oops. Subtract it. Put your lower limit down first. Looks like 4.271. Add it. Put your upper limit 6.05. And your interpretation is exactly the same. Okay, your interpretation is we can be 90% confident that adults spend between, sorry, it's sloppy and I'm running out of space, 4 point. Now notice here, just to let you know, my original mean was given to 2 decimal places, so when I reported it, I took it to 3. 1 and 6.05. Well, I didn't take it to 3 on that one apparently. Sorry about that. Hours per week. No, per day. Wow. Per day with digital media. With digital media. Whoops. Okay. Let's fix that one number real quick, because I should have 5.16 plus 0.889. Yeah, 6.049. This should actually be, I apologize for that. Because again, it's kind of a basic rule of thumb that if your original data is taken, however many decimal places your original data is, take your answer that you're going to provide out 1 additional. So if your mean is given to the hundredths, then take your confidence interval to the thousandths. Okay. And that ends our videos for confidence interval.